In the last couple of videos, we started talking about light energy. So remember, light energy is radiant energy, right? It's only one form of energy. We said that light energy has both wave-like and particle-like properties. If we were to focus on the wave-like properties, we can define light energy based on its wavelength, right? Different forms of radiant energy are going to have different wavelengths. Its frequency, and then we also related energy to that. And then if we were to take all forms of radiant energy, right, all forms of electromagnetic radiation, and put it together in order of wavelength, frequency, energy, we end up with the electromagnetic spectrum. If I was to look at white light, and white light is just what we see when we see light, like we're not seeing a color, so like the sun, light bulbs, that sort of thing. White light is actually a continuous distribution of all wavelengths. For us, it's going to be wavelengths in the visible range because that's what we can see. So it's a continuous distribution of all wavelengths. That's a pretty lame lambda, of all wavelengths. And then we're going to say in the visible range. We can actually separate out those colors. So if you were to take white light and shine it through a prism, we can actually separate it out into the individual colors. So you would see a rainbow, right? We'd have red and orange and all of the different colors separated. So when they're combined, white light, when we separate them out, the individual colors in the form of a rainbow. So we can separate those. By shining through a prism. If we were in lab, you would actually do that. We would use a spectroscope. That's an instrument where we can separate those out. And we end up seeing a rainbow. And then just keep in mind, in a rainbow, right, we don't have spaces between colors. It's not red and then an empty space, right, and then orange and then an empty space. All of the colors run into each other. So continuous distribution, right? We're just separating them out, but it's still continuous, and that's important. If we were to look at matter, so individual atoms also give off light when they're heated or energetically excited in some other way. But if we were to add energy to an atom, what happens is once it loses that energy, it's going to give off light. The light, however, is not a continuous distribution. It actually only consists of a few wavelengths. And the wavelengths of light that it consists of depends on what type of atom it is. So like hydrogen is going to emit different colors than mercury is. Knowing that and knowing what wavelengths they're emitting, that's how we learn a lot of information about atoms. It gives us clues as to where those electrons are. So individual atoms give off light when heated or energetically excited in some way, which I can spell. So in a lab setting, we usually do two different things. One, you actually take a solution that contains atoms, usually ions, and you actually stick it, like a popsicle stick with it on it. You would like stick it in a Bunsen burner and it would turn a color. So you're exciting it with heat. The other one we have is we actually have a lamp where we can put in a vapor tube that has a gas in it, and then you plug it into the socket. So we have some electricity exciting it. So basically we're adding energy to our atom. When we do that, what's going to happen is as it loses energy, that's going to be given off to us in the form of light. Remember, energy is conserved. So we have to give it energy for us to give us back energy, if that's making sense. I'll draw a little picture here in a little bit, and hopefully that'll make more sense for you. The important part right now, though, is that light that it gives off is not continuous. So this light only consists of a few wavelengths, right? It is not continuous. And like you said, this gives us clues. About the atom's makeup. So those colors we see, it's in the form of what's called a line spectrum. And I didn't write it down, but I did say that the light that we get off from one particular atom is different than atoms of a different element, right? Hydrogen and mercury are going to give us different line spectrum. So essentially what this is a series of colored lines and then it's separated by black. You just don't see color. Black is the absence of color. So you would see darkness, right? Because we wouldn't be seeing light. And then you would see a series of colored lines. Depending on what atom it is, you would see a varying number of lines, different colors of lines. You know, sodium is typically one red line. Sometimes you'll see two really close to each other. Hydrogen, you would see four. So again, depending on what type of atom it is, the line spectrum is going to be different. You can kind of think of the line spectrum as almost like a fingerprint for our atoms. By looking at line spectra, you can determine what atoms are present in something. So a series of colored lines separated by nothing, right? It would be black in color. And there are pictures in your text, so please look at those in lab. You would see them also. So what this is telling us, a couple different things, is that when light energy interacts with matter, only certain wavelengths are absorbed and emitted. We're saying that energy is quantized. Quantized is something that exists in discrete amounts. It's things that are not continuous. So let's write all that down. When light energy interacts with matter, only certain wavelengths, so only certain frequencies, only certain energies. We could substitute any of those terms, right? Frequencies or energies are absorbed and emitted. I'll talk about the difference between absorbed and emitted in a few minutes in more detail also. So when light energy interacts with matter, only certain wavelengths are absorbed or emitted. We would say that the energy is quantized. And that's a term that we're going to use a few times. I do want you to know what it means. And it's essentially anything that exists in discrete amounts. So it exists in discrete, right, non-continuous amounts. the example that I usually use is if you're gaining elevation, so you're going up, and you're going up using a ramp. So you're going up on a ramp, or if you're going up using stairs, right? If you're gaining elevation on that ramp, you can step anywhere on that ramp. So you can gain elevation continuously, right? There's nothing to stop you from stepping anywhere. If I was to gain elevation on stairs, though, I can only gain elevation in these discrete amounts, right? I can't step where the riser is. I can only step on the flat part. So I can gain elevation in those amounts, right? Not continuously. So stairs would be something that would be quantized. I can only go up in discrete amounts. I can't hover where there isn't a tread, right? On a ramp, however, though, I can gain elevation continuously. So this is quantized. This is not quantized, right? This would be continuous. That says continuous, believe it or not. So gaining elevation continuously, or something that is quantized. So instead of seeing a rainbow, right, instead of seeing a continuous distribution of wavelengths of visible light, when light interacts with matter, we're only seeing certain colors. So only certain wavelengths, which means certain energies. So I want to look at the Bohr model of the atom real quick, and then we'll do some energy calculations. So our Bohr model. Niels Bohr was the first one. This was, I think, I wrote down 1914, to propose a model of the atom. And it's not the theory that we use anymore. We're going to use the quantum mechanical model. So after our first exam, and we start with the rest of chapter 3, we're going to transition into the quantum mechanics. But it's still important because it was the first model that constrained atoms to specific energy levels. And that part is true. That part does carry into quantum mechanics. So Bohr proposed the first model of the atom. And essentially he thought of the electrons circling, and this is the part that isn't necessarily true, that circles the nucleus. Kind of like planets would circle the sun. So it was based on planetary motion. Quantum mechanics is using the wave-like nature of electrons. Remember de Broglie from our last video, we actually calculated the wavelength of our electron. So instead of just circling it in a nice linear path, we're going to think of the electron as following a wave-like pattern. Bohr, however, had us just circling, so based on planetary motion. But the part, like I said, that we keep is he confined electrons to specific, and he called them orbits because he was basing it on, like planets. So to specific orbits, which we're going to call energy levels. So if I was to draw a little picture of an atom, and keep in mind, remember, this is not even remotely to scale. Remember, my nucleus is super, super dense. So if my nucleus was the size of what I just drew, this line that I did, that's going to be my first energy level, would be like way in the next room. Like it would not be in this room. It would be like in the neighbor's house, right? So we can't really draw it to scale because we would never be able to fit it on the iPad here or your paper. So we're drawing it not to scale. So just keep that in mind. So I can have an electron there, or I can have an electron here, but I can't have it in between. Right? It's kind of like our quantized idea of our stairs, right? I can be on this step, I can be on this step, but I can't be in between. And that's essentially what we're doing to our electrons. Our electrons can be on one, they can be on the other, they can move between them, right? We can go upstairs, we can go downstairs, we're not stuck on a specific stair, but we can't be in between them, and our electrons cannot be in between them. So we're confining our electrons to specific energy levels. And I'm going to call this my first energy level. N actually comes from our quantum mechanics, so I'm kind of mixing two theories here, but N is going to represent my number of energy levels. We're going to use that in an equation I'm going to give you next. So do know that our energy levels are going to be N. And then my second energy level, this is pretty straightforward. If I wanted to add a third energy level, I bet you would never know what it's called. Good guess. N is equal to 3. N is 4 when it's the fourth energy level, and so on. So our electrons can be in those levels. They can't be in between, right? They're quantized. They can move. So I had talked about emitting and absorbing energy. If I was to add energy to this atom, what's going to happen is one of my electrons, or more than one, it just depends, is actually going to move up to a higher energy level. Remember, opposites attract, right? My electrons have a negative charge, my protons have a positive charge, neutrons have no charge, so my nucleus has a positive charge. Things are more stable. When things are more stable, they're lower in energy. So the closer electrons are to the nucleus, the more stable they are, the lower in energy they are. So if I add energy to it, it becomes less stable, it becomes higher in energy, and it's going to move away from that nucleus. Things don't like to be high in energy. They like to be low in energy, if possible. So eventually that electron is going to fall back down to its original energy level. When it does that, energy that is equal to that energy difference between those two energy levels is emitted at us, right? Remember, energy is conserved. So if that electron is going to lose energy when it goes back down to its original energy level, then that energy has to go somewhere, and it's emitted to us in the form of a color. We see it in the form of a color. It can emit ultraviolet and infrared. Also, we just don't observe that. So when we see color, like if I see the color red, if I was wearing a red shirt, what's happening is the dye in my shirt has electrons that are making that transition, right? The light from around us is causing those electrons to gain energy. They're falling back down, and that energy difference corresponds to the color red. So let's try to write some of this down because I know I just said a lot. So our first part is we need to remember is that electrons are lower in energy when closer to the nucleus. Electrons are higher in energy when further from the nucleus. Those two statements we're going to use a lot in this chapter. This section and then also the section that's with Unit 2, those two statements are going to be really important. So remember, things want to be stable. We could say more stable equals lower in energy. Those are always going to be true. So if something's high in energy, it's less stable. If something's low in energy, it's unstable. It's more stable. So more stable, lower in energy. So electrons are lower in energy, right? They're more stable when closer to the nucleus. Electrons are higher in energy. They are less stable when further from the nucleus. So, if energy is added to the atom, so this is, if I scroll back up a little ways, right? This statement right here, when light energy interacts with matter, only certain electrons or only certain wavelengths are absorbed or emitted, right? We had said energetically excited when it's heated, that sort of thing. So that's what I'm talking about now, right? If energy is added. So if we're heating it, if we're somehow energetically exciting it in some way. So when energy is added to the atom, they're gaining energy, right? Energy is not just disappearing. We're not just giving it to the atom. The atom's not going to do anything with it, right? The atom needs to do something with that energy. So if energy is added to the atom, electrons gain energy. And if they're higher in energy, where do they go, right? They go further from the nucleus. So if energy is added to the atom, electrons will absorb that energy. Let's actually put that word in there. And move further from the nucleus. So they're going to a higher energy level. So they could go from the first level to the second, from the second to the third. They could go from the first to the third, but they're moving away from the nucleus because they're gaining energy, and they're higher in energy when they're away from the nucleus. So when energy is added to our atom, electrons absorb that energy and are moving further from the nucleus. Things don't like to be unstable. Things want to be more stable. So eventually that electron is going to move back down to the lower energy level. When it does that, it's losing energy. That energy doesn't just disappear. It's going to be emitted at us. If it's in the visible range, we will see it the color. So when the electron falls back down to the lower energy level, energy is emitted. And then if in the visible range, we see a color. What color we see depends on the wavelength. That wavelength depends on the energy difference between the two energy levels, right? So if I had an electron, if I go back up, if I had an electron fall from 4 down to 2, we're going to see a different color than if an electron falls from 3 down to 2, right? Because the energy difference between here and here is different than the energy difference between here and here. The energy is different, our wavelength is going to be different. So if we add energy to our atom, our electrons absorb that energy and move up an energy level. They're going to fall back down. When that happens, they emit energy, right? Energy is conserved. If it's in a range that we can observe, we're going to observe it, right? We'll see a color. Do you pay attention to these two words, absorb and emitted, right? Up here I use the two, right? Absorbed and emitted. So when light energy interacts with matter, only certain wavelengths are absorbed. That's when our electron goes up. We're not seeing that, right? The atom is gaining that energy, and then emitted is when it comes back down. It's going to absorb and emit the same amount of energy. Let's go through an example calculating the energy that's either emitted or absorbed from an electronic transition. So an electron moving between energy levels. So our first example, we're going to calculate the energy associated with the following electronic transition. So n equal to 4 going to n equal to 2. So I'm going from the 4th energy level to the 2nd energy level. So if I'm doing that, is the energy emitted or absorbed? That is the first thing. So if it's going down in energy level, right, it's going to be emitted. The reason I mention this is because this is a typical type of question, and I know there's some in the more homework where it will give you the actual answer. If it's emitted, it's being given off. So, and I'll write this down in a minute, but it's going to have a negative sign in front of it. If I said calculate the energy associated with the electronic transition of n equal to 2 going to n equal to 4, it's being absorbed. Numerically, it's going to be the same amount of energy, right? If something is going to absorb, and I'm just totally making up a number, and this is going to be way off from what we're going to calculate it to be, but let's just say it's 1 joule, then when it emits energy, it's going to emit 1 joule. The difference between the two is when we write the value, it's going to be positive when it's absorbing. It's going to be negative when it's emitting. So you do have to pay attention, because if the answer was 1, both positive 1 and negative 1 are going to be answers. And I know for a fact there's a more homework question like this, so you can practice it. So be careful. If we're emitting, we're going down in energy level, right? Energy is going to be given off when the atom is becoming, or when the electron is becoming more stable. If we're absorbing energy, it's gaining energy, so it's going to be positive. So before we get into the math, I haven't given you the equation even yet, but I do want you to wrap your head around these signs. So energy, the sign, because we can't have a negative amount of energy. So if you see a negative value, a negative sign in front of energy, it just means direction. So for energy, the sign gives direction. It doesn't tell us where on the number line it is. -1 and 1 joule are exactly the same amount of energy. -200 joules and a positive 200 joules are exactly the same amount of energy. The negative tells us the direction, not where on the number line, right? Not the magnitude. So for energy, the sign gives direction, not magnitude. Positive 200 and negative 200 are the same thing when it comes to energy. So the sign gives direction. A negative value on our energy, so negative energy means we're losing energy. So in this case, emitted, right? The electron's going down in energy level. A positive value means it's gaining. Which means our electron's going up in energy level, so absorbed. So this is going to be true anytime we talk about energy. The sign on energy is always going to give us direction, not magnitude. If we're solving for wavelength, frequency in this chapter, or any chapter, those are always going to be positive values. So wavelength and frequency will always be positive values. I'm going to add a second part to this question to calculate our wavelength. So wavelength and energy will always be positive. That's also important to note. And let's just add that second part now before we forget. So calculate the energy associated with the following electronic transition. And then we want to know what is its wavelength. The equation that's on the back of your periodic table is this one. Your book does it slightly different, and we can do it the way that your book does it also when we're done if you want. The way the book does it is how I taught it for years. I didn't start doing it this way until I moved here. So this equation is for calculating the energy at a specific energy level. So N is that energy level. So if I wanted to calculate the energy of the electron at the second energy level, I would plug in 2 for N. If I wanted to calculate the energy of that electron at the fourth energy level, I would plug in 4 for N. If I wanted to calculate the amount of energy emitted when it goes from 4 to 2, I would do both of those calculations and then subtract them, right? Remember, the energy is equal to that energy difference. So what we're calculating here is that energy difference. Delta means change when we write it this way. So capital delta, change in energy. It's going to be my final energy minus my initial energy. So essentially, we're going to do this equation twice. Once plugging in 2 for N, another time plugging in 4 for N, and then we're going to subtract them to get the difference. As far as which one gets subtracted from which, I don't think of the final and initial. What I think of is this whole, should it be positive or negative? So subtract it however you want, and then add the appropriate sign. So since this is being emitted, right? I'm going from 4 down to 2. It's losing energy, so I need it to be negative. So when I subtract them, I want it to be negative. If I would have said I'm going from 2 to 4, then energy is being absorbed, and I want it to be positive. So again, this sign is going to be important, and it depends on the direction. So our math. So if I'm just going to substitute N with a 2 here. So when I'm at the second energy level, negative 2.18 times 10 to the negative 18th joules multiplied by 1 over 2 squared. Don't forget to square it. And then I'm going to set them both up at the same time. My energy at the fourth energy level, a negative 2.18 times 10 to the negative 18th joules multiplied by 1 over 4 squared. Right, we're plugging in 4 for N, don't forget to square it. So I'm gonna grab my calculator and type those in. Hopefully you guys will do the same. And for this first one, I got a negative 5.45 times 10 to the negative 19th joules. The 2 and the 4 are exact numbers, so it's the 2.18 is the only thing you have for significant digits here, so 3. So I'm typing in the second one here. And I got a negative 1.36 times 10 to the negative 19th. And I'm gonna double check that first one real quick. I don't have you guys checking my math, so I wanna make sure I did it right. I was talking while typing stuff on my calculator, and that's often a recipe for disaster, which I'm doing again. Yep, got the same thing. That's good. Okay, so this is my energy at the second level, my energy at the fourth level. I want my change in energy, so I'm going to subtract them. Again, for me, instead of trying to think which one gets subtracted from which one, like I just don't want to mess with that. I just know that I'm emitting energy, so it needs to be negative. So I'm going to subtract one from the other. If it comes out positive, I'm just going to throw a negative sign in front of it. So I'm going to do the negative 5.45 times 10 to the negative 19th joules. From that, I'm going to subtract. Be careful here, you're subtracting a negative number. 1.36 times 10 to the negative 19th joules. So this is going to be an energy difference. We don't know if it's the right energy difference. The magnitude will be the same though, right? So minus a negative. Don't forget to type that in correctly. We don't want to be. And I end up with a negative value, so we know we did it in the right direction. If we didn't though, you would just throw that negative in front of it. So I give off, right? The negative sign just means it's being given off. We are giving off a positive 4.09 times 10 to the negative 19 joules, right? There's no such thing as a negative amount of energy. So I'm giving off a positive amount of energy. That sign tells me I'm giving it off. That's all that sign means. So we're emitting 4.09 times 10 to the negative 19th joules. We did add a part where we're going to calculate our wavelength. So I'm going to do that next. So these are equations that we've had from the last couple of videos. We know that energy is equal to Planck's constant multiplied by frequency. And we know that the speed of light is equal to my wavelength multiplied by my frequency. Again, these are on the periodic table as well as the two constants, right? H is Planck's constant. And C is our speed of light. So you can either do it in two different ways, right? This is my energy, this is E. So I don't have an equation. If I look at my two equations, I don't have one that has both wavelength, which is what we're trying to solve for, and energy in the same equation. So I can use the first equation there and solve for frequency, take that answer and then plug it into the second equation, or we can rearrange the first equation and substitute it into the second. However you want to do it is fine. So I'm going to do it the first way with the substitution. If you want to do it in two separate steps, by all means do it that way. So I know that my frequency is going to be equal to energy divided by H, right? I just took this equation. I wanted to get frequency by itself, so I divided both sides by Planck's constant. I'm then going to take that and I'm going to substitute it into that equation. So C is going to equal my wavelength multiplied by my energy divided by Planck's constant. If you want, you can then rearrange that so wavelength is on one side of the equal sign. To me, mathematically, it's just as easy to plug it in. So I'm going to start substituting my numbers for my variables. So 2.998 times 10 to the 8th meters per second, that's C. That's equal to my wavelength, which is my unknown, multiplied by my energy. Note that I'm dropping that negative sign, right? The negative is not the value of my energy. It's the direction, and we're not going to plug in our direction. Also, if we go back up to this statement, wavelength and frequency always need to be positive values. If I was to include that negative sign when I plugged it in, it would come out to be negative. I can't have a negative wavelength. So even if you forgot to drop the negative, when you get your answer, drop the negative. Otherwise, it makes no sense, right? Going back up one more time, making you guys dizzy. Wavelength and frequency are always going to be positive. And then that's divided by 6.626 times 10 to the negative 34th joules times seconds. And again, those two constants are also on your periodic table, so you do not need to memorize those. Those are allowed for you to have. Units, my joules are canceling. These seconds are going to end up canceling, so I'm going to be left with meters as my answer. So, or as my units. So plugging stuff into my calculator. Hopefully you guys are playing along again. This one's taking me a little bit because I goofed it up while talking. And I ended up with 4.8. But I have three significant digits, so 86 times 10 to the negative 7th meters, which is 486 nanometers. This is in the visible range. Electronic transitions that end in the second shell are in the visible range. So this is in our visible range. We would see this color. The problem didn't ask us to convert it to nanometers. I just did, but that would be my wavelength. Again, if you wanted to just do it 2 times, do this first one, solve for frequency, and then plug the number in instead of, the symbols, that works too.